Now that we know the formula for the range of a projectile, we shall look at some of the applications. So as you can see, this is the expression for the range. The range is equal to V0 square divided by G multiplied with sine of 2 theta. Now a beautiful application here is, because of this 2 theta part, that if you study again trigonometry, you shall come to know this, that sine of 180 degrees minus of theta is the same as sine of theta. So if say theta is 60 degree, then sine of 180 minus 60, that is 120 degree, is the same as sine of 60 degrees. This is the application which we shall be using here. So if I write this like this, instead of sine 2 theta, I am writing it, in place of theta I am writing 90 degree minus theta. So what does this become? This becomes V0 square by G multiplied with sine of 180 degree minus 2 theta, and using that one, therefore this is the same as V0 square by G into sine 2 theta. So what I am trying to say here is that the range of a projectile, that is how much height it can go, distance it can go, it is the same whether you launch the projectile at theta or at 90 minus theta, and that is because of this 2 that is there in the multiplication, because that makes this 180 and sine 180 minus theta is same as sine of theta. So if you have a projectile and suppose initially you launch the projectile at an angle of 30 degree and say it covers a distance of 100 meters. If now you launch the projectile at 90 minus 30, that is 60 degree, it will cover the same 100 meters, because sine of 2 theta, that is sine of 60, is same as sine of 180 minus 2 times 60, that is 180 minus 20, which is again 60. So this is the application of the range of a projectile. Now as you might have guessed by now that when we derive this equation, just like all the other cases, this is the expression for what happens in an ideal case, not in a real world. That is, when we derive this equation of the projectile motion, we assume that there is no friction in the medium that it's moving, there is no air resistance, that the value of acceleration due to gravity remains fairly constant. But in real life, this kind of situations, they won't hold always, because we know that air has got a resistance, there is some frictional and resistive forces coming to play, because of which the equations will slightly change. But the equation of the projectile that we derived last day, that remains more or less constant, provided that this value of G remains the same. Now when does value of G remain the same? So if this is my earth and this is the atmosphere of the earth, your projectile should not go this much high into the atmosphere, because the value of acceleration due to gravity changes with height of the atmosphere. G at any height of the atmosphere is G at ground times 1 minus 2 times the height of the from the ground that it has went up, divided by radius of earth. Similarly, your projectile, if you launch it from here, it should not go a long way and fall somewhere back there, because if it does this, the latitude at this place is not same as the latitude at this place. The latitudes are different. And again, as you should study in the chapter of gravity, that the value of acceleration due to gravity, it also depends upon the latitude and the angular speed of the earth. So G will change, and thus the equations that we derived shall no longer hold. Therefore, for the equations to hold true, 3 conditions have to be met. First of all, the height of the projectile should not be considerably large. The range of the projectile should not be considerably large. Finally, the initial velocity with which we launch the projectile should not be very large, because if this is large, then there will be friction and air resistance. If this velocity is small, the air resistance and friction shall also be small. Now we shall be doing one classical problem here. Let's just start the problem. So this problem, it's problem number 41 from the example in my book. It's a very classical problem and interesting one too. It says that a hunter aims his gun and fires a bullet directly at a monkey on a tree. At the instant the bullet leaves the gun, the monkey starts falling freely. Will the bullet hit the monkey? Explain. Assume that the muzzle velocity of the bullet is sufficient to hit the monkey. Alright, so this is the diagram that they have provided. So here is the y-axis, this is the x-axis. Suppose at this point A, the monkey is located. They have named a point like this to be B, where the projectile reaches, and initial velocity have been assumed to be u, and this direction has been assumed to be theta. This point has been named C, this point has been named O, and this is x and this is y. Fine. So what's happening here? This is the y and this is the x-axis, the two axes. From the point O, here the hunter is located and fires the gun at the point O. This point here is B and this point here is A. What's A? A is where the monkey is initially seated, that is before the bullet is fired. As soon as the bullet is fired, by the sense of reflex, the monkey lets go of whatever it's holding and starts falling freely in this direction where the gravity is acting. And this is the projectile, the trajectory of the bullet, which has been fired with the initial velocity u, inclined at an angle theta with the horizontal, and after some time t, any arbitrary time, it covers a distance x in the horizontal direction and a distance y in the vertical direction. We shall have to find out as to whether this bullet will hit the monkey or not, provided again that this thing is everything like frictionless and air resistance is negligible and so on. So that is what we will be finding out in this case. Okay, so first of all, when the monkey is falling down freely, in any time t, it has covered this distance. So what is the distance that the monkey has fallen? Height of monkey is equal to initial displacement h0 plus initial velocity times time plus half at squared. It has no initial displacement, it is simply sitting there just like that at rest. What's u? Initial velocity, no initial velocity, it is at rest. So the only thing that acts on it is the gravity, and when it has fallen for a time t, this is the height that the monkey has travelled in the downward direction. Coming back to the projectile, what's happening here? Well, we know that velocity along the x direction is u cos theta, velocity along y direction is u sin theta. And we also know this, that the distance it travels, x, is equal to u cos theta into time. From here we find time is x divided by u cos theta. And what about the y direction? In the y direction, what it has travelled? Well, y is equal to velocity along y, that is u sin theta into time, and it's against gravity, so minus half g time squared. If we substitute the value of time, this becomes u sin theta into x by u cos theta minus half g into x squared by u squared cos squared theta. So that is x tan theta minus half g x squared by u squared cos squared theta. This is my 1. And this is nothing different, this is exactly what we expected here. Now let us look into this portion. Let us consider this triangle here. Which triangle? Triangle OAC. In this triangle, what is the value of tan theta? Tan theta is this portion AC by the base OC. And what is AC? AC is AB plus BC, and that is equal to OC by multiplying here, it's OC tan theta. Okay. What is AB? Okay, let us keep it AB like this. And what is BC? BC is the Y, the distance which we have considered to be Y in our diagram. And what is OC? OC is X tan theta. Therefore, what is AB? Again, AB is the distance the monkey has fallen. That is simply x tan theta minus y. So far so good. Now we will substitute the value of y from here. That will give us AB to be x tan theta minus x tan theta plus half gx square by u square cos square theta. This cancels out. So AB is equal to gx squared by 2u squared cos squared theta. This is AB for the projectile. Now for the monkey, what's the height? It's half gt squared. And what is time? X by u cos theta. So it's gx squared by 2 u squared cos squared theta. So we again did what we did during the derivation. During derivation, if you remember, we considered the motion along x-axis and y-axis separately, and then we combined them to find out the equation of motion for the projectile. Here also, we considered these two motions separately. Initially, we considered simply the monkey falling down, and then we used the equation of projectile motion and obviously some basic geometry here, some basic trigonometry, to find out that AB, the distance, using the equations of projectile comes out to be this. Now the time for which this bullet has been in motion or in flight is same as the time for which the monkey is falling. So therefore I can substitute this expression of t here from here, and we see whatever is the height the monkey has fallen, that is the same height by which the projectile has come down due to gravity. So at the point B, it exactly hits the monkey. So if there is no air resistance and if there is no friction, and you fire a bullet and at that instant the monkey lets go of the grip, it will get hit. So what can the monkey do? Well, first of all, it can do one thing, which is never let go of the grip. Whoever fires the bullet at you remains seated at your place. In that way, the bullet will never hit because it will curve downwards. That's true, but obviously we know that because of the reflex they will let it go. So in that case, they should at least let it go a few seconds after the bullet is fired. If they let it go instantly, it's going to hit the monkey. Now you might wonder if this is true or in the entire thing is theoretical. But yes, this is true. When any kind of operations take place either in the wars or for the simple hunters, you must have heard of snipers and all. So if you look in the internet, you shall find out that when snipers, they take long distance shots. They're located in some remote location in stealth mode, and suddenly they fire the bullet. So when they do take into account what is the speed of the wind in that place, what is the humidity of the air, what is the resistance that the air will provide, and using that they correct their equations so that if they hit someone, it goes and hits the person. So if you are wanting to hit the monkey such that the monkey does not move from its place, if you know that the monkey will remain seated at its place, you should not aim at the monkey, you should aim somewhere here. Then it will curve down and hit the monkey. If you aim exactly at the monkey and the monkey doesn't move, it will not hit the monkey. There is one limitation in this, and that is when you shoot it, the value of u should be sufficient. If u is small, then what will happen is it will come down and bend even before this point C. In that case, even if the monkey lets go at the same time as you fire the bullet, it's not going to hit, because your range is not enough to reach the path along which the monkey, or in this case our prey, is falling.